So begin recording. Okay. I hope you guys are doing well. Yes, so I think most of the people who are logged in and watching this have taken the exam, but if you have not taken the practice exam on HackerRank, you have until tonight to do so. So make sure you you take care of that. It just counts as a homework, and again, the practice exam was I intentionally selected easy problems. I probably should have done a mix of problems to kind of get a feel for it. But that's it seems to be okay. And probably what's going to happen for the final exam itself, which is scheduled for Tuesday of finals week, I'll probably have two available times. Probably I'm thinking 10 a.m. and 10 p.m. California time, and we'll probably have kind of we'll make the exam available during that time to take the exam. So, well, maybe I might have to adjust it a little bit, but those I'll probably pick some times to run it. Okay, so today I just have a couple of notebooks here, and this just shows some basic, very basic data modeling things that you can do in Python. So first we'll run through stats models, and then I will also run through the most basics of Scikit-Learn. Okay, so base Python does not come with any functionality for performing statistical analysis. So if you want to do something like linear regression, you cannot do it in base Python. You have to import a couple of libraries. Okay, not a big deal, right? But you got to import. So like if you start up R, you've got LM right off the bat. It's available for you. Base Python, not so much. So so there's a few things that can be done. There's stats models. Okay. And you can read about it, statsmodels.org, and this provides you some stuff. And there's information on kind of getting started, along with different documentation and examples here. Okay, so you want to fit like classical statistics models, like linear regression, like logistic regression, any of these kind of, an Anova analysis and things like that. Classical approach, stats models is going to be the tool to use. Okay. There's another thing, Scikit-Learn. Okay, and this is for machine learning. Okay, and I don't know if any of you are in my 102B class, but you have a few, we've talked about classification and regression and clustering and dimensionality reductions, and these are kind of the key pieces of machine learning. And Scikit-Learn has a bunch of tools that allow you to do machine learning in Python. Okay, and it's a very popular thing. There's also it also comes with tools for model selection. This will be things like cross-validation, and it will also have things for pre-processing for like scaling your data and cleaning up your data and things like that. And then it's got a bunch of models that can be fit. So anyway, we'll start off with the classical models. I am not sure. So we have a mix in this class right now. We have a mix of freshmen, sophomores, juniors, and seniors. So I'm going to be talking about stuff, and there's a good chance that you have not yet taken like 101A or 102B or any of these things. And so these, as I mention these models and talk about them, they might be unfamiliar to you. And that's okay, all right? We're just scratching the surface, and I'm just showing that these things are available and can be done as far as, just getting started with some kind of data analysis with Python, right? So this is where we're beginning, and this is not a full in-depth data analysis course. So, but I just wanted to kind of introduce these intro topics. Okay, so anyway, to get started, we're going to import NumPy, we're going to import pandas, we're going to import matplotlib. There's another package called Seaborn that's used for visualization, and I didn't really cover that, but it's available. There is stats models and stats models formula, okay? So I'll explain the difference. So stats models formula resembles R's formula notation for creating linear models. You'll do things like Y as explained by X, okay? And then stats models API uses kind of the Scikit-Learn format where you have an input matrix X and a set of target values Y, okay? So I'll demonstrate both of these here for you. Okay, so anyway, we import all of these libraries here, or modules, okay? And here I'm going to create two very, very simple arrays, okay? We've got 1, 2, 3, 4, 2, 6, 4, 8, okay? X is 1, 2, 3, 4, Y is 2, 6, 4, 8 in NumPy, right? And then we are going to create a scatter plot, okay? So I'm going to use marker dot to do small dots, and then let me just show you. And so this is what our plot looks like, okay? 1, 2, 2, 6, 3, 4, 4, 8, okay? Those are our 4 points, and we want to fit a linear regression line to this, okay? So I'm going to make a pandas data frame out of this. Pandas.dataFrame, X is X, Y is Y, and there's our data frame. Okay, you can do a visual exploration using Seaborn. There's a linear model plot. X is X, Y is Y. The data comes from the data frame, which we have called D. And here it creates a plot. It kind of changes the scaling of the axes, but here it's got this, and then it fits a line, okay? And it also gives us, this is kind of your confidence bound for where the line could be. All right, so so very simple. If you fit a linear model plot in Seaborn, Seaborn has this philosophy that that the package should only be used for visual exploration and not for any kind of analysis. So there is not even a way to extract the slope and intercept of this linear model line, this line. So if you want to get the slope and intercept for the line, you have to use something like stats models, okay? So first we're going to use stats models formula, okay? So we've got stats models formula.api, okay, and we're going to abbreviate that as SMF. Okay, so this is stats model formula API, and then there's OLS for ordinary least squares regression, and we say the model is Y tilde X, okay? So if you have done linear models in R, like in the course 101A, you would be very familiar with this notation, Y tilde X. If you have not done this, then this might be new and unfamiliar to you. And the notation here is basically the outcome variable Y is explained by, that's what this little tilde is. So the outcome variable Y is explained by the input variable X, okay? And if you have multiple x variables, right, you had like a x1, you can have an x2, and an x3, and you can say this output is explained by x1 and x2 and x3, and it would fit coefficients, you know, slope coefficients for each of these terms, x1, x2, and x3. So again, I'm not assuming that anybody has already taken 101A, but I am assuming that you've all fit linear regression models, at least in your like intro stats, stats 10 class or AP stats class. So you are familiar with linear regression, having a slope, having an intercept, okay? So anyway, this is how we create the model, and we're gonna take the output of this and store it as model. Oh, what did I do? Oh, x1, yeah, okay. So y is explained by x, okay, that's our model. And let's print our model, okay? And it says, this is an object, right? So we get some kind of, this is the notation that Python prints out for objects of a certain class, right? So this is a stats models regression linear model OLS class object, all right? And if we want to see what it looks like, what we can do is we have to kind of actually fit the model, okay? So the coefficient, so this initializes the model when we create this. This initializes the model, but it doesn't actually do any computations, okay? So to do the computations, you say model.fit. Now this is, it feels a little strange to do this, but basically you say, well, we've initialized the model, and what we want to do is we want to have it fit, figure out what is the slope, what is the intercept, right? For an ordinary least squares regression model, there's only two parameters to estimate, the slope and the intercept, and so we're going to say estimate those parameters, okay? And it does that, and we've stored the results here. We can ask for the results, and it doesn't look like anything again. This is just the regression results wrapper class object, and so finally, to take a look, we call results.summary, and it prints out this table. So this is the results of your ordinary least squares regression, okay? If you have a more complicated thing, fit will estimate all the parameters and things like that. So anyway, ordinary least squares regression, we only have two coefficients, the intercept and the slope. The intercept, we can see the coefficient is 1.0, and the slope for x, the coefficient is 1.6. It gives us a standard error and a p-value associated with each of these things. So, you know, we only have 4 data points. So the slope of 1.6 only has a p-value of 0.2, okay? Indicating that maybe the slope is not significantly different from 0, okay? You know, with only 4 data points, is there really correlation between x and y? The correlation is 0.8, but is there really a correlation there? And the answer is maybe. We're not sure. We only have 4 data points, so it's hard to say. Okay. It also gives you, so there's a ton of information that comes in this summary table. It gives you confidence intervals for the slope and confidence intervals for the intercept, and we can see there's quite a wide range. It goes from around -9 to +11, and -2 to +5.25 for the slope and intercept. It lists off of other stuff, okay? So the r² value is 0.64. The correlation is 0.8, and the r² value is 0.64. It gives you the F statistic, the F probability, all of that, all kinds of stuff, right? The degrees of freedom of the residual in the model, and things like that. Okay, and so this is the results of fitting a linear regression model to just this very simple data set. Okay, and obviously if you want to do something more complicated, you can add more variables and things like that. Okay, if you want, you can also create the AB line plot, right? So this is stats models graphics. It comes with its own graphics set of functions. And so we've got AB line plot, and we'll add the scatter. We'll add X line, and there you go. It just adds the linear regression line there. Okay. If you want the Anova table, you can say stats models, there's the Anova table on the results, and you get your traditional Anova table with the degrees of freedom, the sum of squares, the mean squares, your F ratio, and your p-value, okay? And so again, if you haven't taken 102A or 102B and you're not familiar with the Anova table for linear regression, you know, this thing might not make a whole lot of sense to you, but that's okay, all right? So these are all these are all important tools in the statistician's tool set that exists, okay? If you want to make a prediction, you can say, what is a prediction if I plug in x equal to 2? So you do results.predict. You give it a small dictionary of your input values. And again, if you have multiple values, x1, x2, x3, you'd have a dictionary where all of these things are defined. And it says the prediction is 4.2. Okay. There is another way of using stats models, okay? And you can do, you can fit, so you can fit it using an OLS, okay? So what we're gonna do, so what we did over here with stats models formula was we had y tilde x, and we're gonna basically do the same thing, except we're going to use the array notation. So the array notation, the way it works is you are going to have a matrix representing all of your x values, okay? So here our x values are 1, 2, 3, 4, okay? And I hope I can talk about this, but when we fit a linear regression model, what we're doing is we're saying y hat, or we're saying y is the result of an intercept, which is b0, plus the slope, b1 times the x value plus error, right? So as far as the model goes, we need to have a column of constants, which is just going to be ones, to talk about the intercept, right? So as far as the intercept goes, we need to have a column of ones, and then the x value is going to be a column of 1, 2, 3, 4. Okay, and when we fit the regression line, what we want to do is we want to predict y. We want y based on basically we're going to have a B matrix, which is the coefficients put together, B0 and B1 together, multiplied by our input matrix X, okay? I am not sure if you are familiar with the kind of matrix notation for linear regression. And if you're not, again, that's okay. I'm introducing it here because this is how Scikit-Learn does all of its models. All of its models are fit using a matrix, and a matrix of inputs X and a column of outputs Y. At least all of its regression and classification models go that way, right? So, so you have your input matrix X, your predicted values or output values Y. And so here we're going to say fit an OLS model, okay? So in NumPy notation, OLS is all caps. You've got your output, the values you're your target values Y, and then your input matrix X. Here, capital X is the matrix where there's a column of ones and a column of the X values 1, 2, 3, 4, right? And if you had more X values, you'd have a column for X1, a column for X2, a column for X3, so on and so forth. So I run that. So you define the model, and then you do model.fit, and then you call results, and you'll notice these results, if you look at this table, is exactly the same as these results, okay? So the two tables are exactly the same. The difference is how we define the model, okay, or how we called the model. So here we needed to have a matrix of input values and and we give it y, okay? Whereas over here, we use kind of the formula notation. So stats models allows for both kinds. So if you're coming from R and you're familiar with linear models, this is going to feel more comfortable for you, okay? A lot of people are coming from the Python side using Scikit-Learn, and this notation might feel more comfortable for them, okay? But I want to introduce this here because we're going to go to Scikit-Learn and everything is in this format, okay? Everything's in that format. Okay? All right, if you wanted to use linear algebra, you can. Here's your input matrix X. The linear algebra solution is X transpose X inverse X transpose Y. This is something that you'll encounter in, I think, 100C, okay? 100C as the solution for linear regression. And if you wanted to do that, you can do X transpose. This is matrix multiply X, X transpose in X, and then you call linear algebra inverse to get the inverse of that matrix multiplied by X transpose Y, and you will get your coefficients 1 and 1.6 as far as the coefficients go. Okay, you won't get any of this other stuff though. So, you know, use stats models, and it provides a very detailed summary table, which is good. Okay, I don't know. Do you guys have any questions on this? This is just the very, very, very basics of starting to use stats models to fit your classical statistics models like linear regression. And you know, if you wanted to do something, you could just type in stats models, logistic regression, all right? And you just go, oh, okay, how do we do this, right? Should ask for an example. Logistic regression in Python, let's see. So we've got, you know, you have a new, better version. Oh, okay, great. So let's take a look. What's logistic regression? And yeah, all right, so there's going to be some, you can kind of walk through all of this stuff, right? So confession time, right? So as far as classical statistics models, I think it's hard to beat R, okay? As far as classical models and statistics, doing things like linear models, linear regression models, logistic regression models, in my opinion, it's hard to beat R, its interface, its functionality. So I tend to default to using R when I'm doing some things from a classical statistics perspective. You know, not to say, okay, stats models is an excellent package. And certainly if you don't know any R and you need to do linear regression, logistic regression, it's certainly possible to do it with Python, not having touched R, okay? Over here, I'm gonna introduce Scikit-Learn, okay? Scikit-Learn is you can just import sklearn. Now, Scikit-Learn is a huge package, okay? There's like so much stuff. You can import the entire thing. But for now, we just want basic linear model regression, right? So from Scikit-Learn, you can kind of go into regression, and you can see these are all different kinds of what we could consider supervised learning, okay? So you've got linear models, all right? So you've got, from linear models, you've got ordinary least squares. You also have ridge regression, you have lasso, you have elastic net. I'm not sure what multitask lasso or multitask elastic net is. And again, if none of these, if you've never heard of any of these things, don't worry about it, okay? These are all just like different things that are being developed for machine learning. Some of these have been around for a long time, like ordinary least squares regression has been around for a long time. Lasso and ridge regression have been around for a while as well. But then also somebody will just publish a paper, and Scikit-Learn is pretty quick about like coming up with some kind of quick implementation of it, right? So you have logistic regression, and then you have different things, right? You can fit in gradient descent and stuff, okay? There's linear and quadratic determinant analysis, kernel ridge regression, all sorts of stuff, support vector machines. These are all different topics that would be covered in like a machine learning course. Also, there's kind of classification things that can be done, like support vector machines and all sorts of stuff. But anyway, today we just want the simple linear model and ordinary least squares regression, right? So what we're going to do, okay, is we can just kind of follow this example right here. So here, this is what I'm going to do. So I'm going to import. Let me restart and clear out my outputs. Is there a machine learning stats course at UCLA? Yeah, I teach. So the way I teach my 102B, Stats 102B class, I teach it like a machine learning course. Not everybody teaches it that way. The title is called Computation and Optimization, and I kind of use it towards covering the computation and optimization aspects of machine learning. But other teachers might take a little bit more of a kind of a matrix-based approach. Certainly, I use a lot of matrices in my 102B class, and we cover matrices a lot. But I cover a lot of these kind of machine learning topics. 101C also, Stats 101C also covers a bunch of these different models, machine learning models, and talks about them and their applications. But there's less of a focus on the algorithms themselves, whereas my 102B class focuses a lot on the algorithms and writing that code. So there's lots of stuff out there. Anyway, so I'm going to import a linear model from Scikit-Learn. And here I'm going to just generate some random data, right? So I'm going to just do some random numbers multiplied by 10. So NumPy random rand will give me 50 values between 0 and 1. And I'm going to multiply that by 10. So I'm going to get 50 values between 0 and 10. And here, the true model is 1 plus 0.8 times x. And then we're going to add some noise. So this is random n, rand n. This is standard normal values. So these will be like 50 values between, where 95% of them are between -2 and +2, and almost all of them are between -3 and +3. And that we add that noise to get our y values. And I'm going to get a scatter plot of x and y. And let's go ahead and plot that. And this is what it looks like, okay? If we look at y, it is it's a one-dimensional array. A one-dimensional array. It's not a matrix. Okay, it's a one-dimensional array. And what we want to do is we want to create a model that is going to predict these values in y based on our input values of x. Okay, and so to create this, we're going to call from linear model. We're going to do dot linear regression. Okay, so that's ordinary least squares is linear model dot linear regression. And here we're going to say fit and intercept. Okay, if this is false, then what I would have to do is I would have to alter my x matrix to include a column for the intercept. Okay, so we're going to do linear model dot linear regression. We want to fit the intersect. Okay, so the model, this is just kind of what the model looks like, and x right now is just a one-dimensional array. one-dimensional array, 50 values. Okay, and so if we want to use Scikit-Learn, okay, it requires that the feature matrix, okay, that your X matrix, X be a matrix and Y be a one-dimensional array. Okay, so Y is correct in that it's a one-dimensional array. X is not correct because it's a one-dimensional array. X needs to be a matrix. So we got to reshape it. We've got to reshape it to be 50 by 1, right? So we call reshape 50, comma 1, and this will make it a 50 by 1 matrix. Okay. So once we've done that, we have our model here, linear model, linear regression fit. We're going to call model fit x comma y. Okay. So this part right here, model fit x comma y, is very similar. Oh, I already closed it. Very similar to the matrix notation that we used in stats models, not the formula API, but the regular stats models API. So we have kind of our input matrix X and our target values Y. The difference here is that this input matrix X does not include a column of ones, and we don't have to include the column of ones because we have the option of saying fit and intercept to be true. Okay, so I've done that, and you can get out the coefficients and the intercept, okay, from the model. And so you can do model.coef underscore. And the intercept is this, right? So this would be the slope, and this is the intercept. And we can see it resembles the original is 1 and 0.8. Those are the true values in the population. And we're getting something like this, okay? Now, Scikit-Learn, there's underscores here to kind of indicate that these are values that are stored in this class object, okay? In the model, we have an instance of this class object.
Yeah, she told me.
Oops.
So the thing is, they wanted a bigger apartment with a bigger bedroom, so they can have, you know, three folks on one bed on one side and two the other side. And the date would be September because we already have paid.
All right, it's okay. Someone, I don't know what happened. Okay, that's all right. I think I muted everybody, but can you guys still hear me? I think. Okay. The model okay, so these are values that are stored inside the instance of the model, okay? But yes, the coef is an attribute of the model, okay? So these are values or attributes of the model, but they have an underscore, which is kind of the, when you define your class, it's kind of an indicator, or it's completely optional to put this, but the kind of the convention is if you put an underscore after the name of your attribute, it means you're not supposed to interact with it directly, okay? So I don't know if you guys remember, we were talking when we developed the classes for poker hands and things like that. I think one of the attributes was cards, and we would do like cards underscore. And it just kind of means you're not supposed to interact with it directly, right? So like you can, but you shouldn't, okay? So, and again, stats models, not stats models, Scikit-Learn, it's mostly for, there's kind of different philosophies as far as fitting a model. And Scikit-Learn and machine learning in general is all about predictive ability and less about interpretability, right? So if you compare like linear regression to a neural network, they are on opposite ends of the spectrum, right? So, you know, I don't think you've learned about neural networks yet, but neural networks are these models that have very, very good predictive abilities, right? You put in some inputs, you run it through the neural network outputs and says, we're gonna predict this, we're gonna predict this, we're gonna predict this. And it's very good at it, right? It's very good at making predictions. You can give it a picture of a cat and it's gonna say, that's a cat. You give it a picture of a dog and it's gonna say, that's a dog. And neural networks, incredibly good performance. However, if you open up a neural network, there's going to be like hundreds of coefficients in there, thousands of coefficients. And if somebody says, hey, what does this coefficient mean? No one's going to be able to tell you what it means, okay? The interpretability of the coefficients inside a neural network are completely lost, okay? There's all these different nodes. Each of these have different weights and matrices associated with them. It's impossible to interpret a neural network, okay? Linear regression, on the other hand, even at your introductory stats class, you learn about how to interpret the intercept and the slope. You say the slope is, if you increment x by 1, your prediction for y goes up by the amount of the slope. So if the slope is 0.8, that means if one person has an x value of 5 and another person has an x value of 6, our prediction for the person with x6 is going to be 0.8 more than the person with x equal to 5. Okay, so there's very clear interpretability with linear regression. Okay, and even in a multiple linear regression where you have multiple x values, each of those will have a coefficient, and you can say like, oh yeah, when predicting the cost of a house, you know, each square foot that you add, you know, adds $70 to the value of the house. Each bedroom you add to the house adds, you know, $1,000 to the cost value of the house, and things like that, right? So there's high interpretability. Scikit-Learn falls on the machine learning side, where it cares less about interpretability and more about predictive power, okay? So things like getting the coefficient and the intercept are less important in Scikit-Learn's philosophy, and it intentionally kind of keeps these hidden. These are not meant for the user to kind of interact with, all right? It just kind of, it's more so about, let's fit the model and let me make predictions based on the model, okay? So here, there's a lot of stuff where you can get predictions, right? So here we're gonna, I'm gonna just take some new values from 0 to 10, and we're gonna say, what we wanna do is we wanna make predictions for these 21 values from 0 to 10, okay? Now in order to make predictions, the x values always have to be in the form of a matrix, right? So the shape of this matrix is going to be 21 rows and 1 column, okay? But notice what I've done here is I'm going to reshape this matrix, okay? And instead of saying I want 21 rows and 1 column, what did I do? I did -1, comma 1. And what that means is basically -1 is you are telling Python, figure out how many rows you need, right? So if I did not print this out, okay, right? So let's say I did like linear space, and it did something like vi equals, all right, what is it? Step? I forget. Step equals 0.5. Is that going to work? No. I forget how to do this. Okay. Space. How do you do your step size? Is there a step size? Stop number. Start, stop, number, endpoint. Oh, wait, step, restep. Okay, I guess you don't get to specify your step size. Okay, but you know, if I did something and I didn't know it was length 21, okay, you know, I don't want to have to take, if I don't want to figure out exactly that this needs to be 21, I can just put in -1 and Python will reshape it so that it works, okay? So for example, I could just do -1 and say I want 3 columns, okay? And then it's going to, and it would figure out that, oh, you know what? We need to have 7, right? And you can give it something like, if you give it 4, it's going to say it can't reshape it into that size, right? But here it allows you to reshape the thing without having to specify every single dimension, right? Like if you do like this, it's going to say like, you can't do that, and you go, well, I forgot how many rows I had. So -1 is a very convenient thing, and you'll see it a lot in other people's code, okay? So I just want you to know, what does it mean you're reshaping it with -1? -1, maybe I'll add this, okay? -1 means tells Python, or tells NumPy to figure out how many, what value it should use. Because the human was too lazy to figure it out themselves. So it's convenient for the human, okay? All right, so now that we've reshaped X into a 21 by 1 matrix, we can say make a prediction using model.predict and the input matrix X, and it says, oh, these are the predicted values. We can create the scatter plot, and we can also plot the prediction versus the predicted values, and we're gonna do color red. All right. And so we can say, all right, so this is the original scatter plot. We've added the prediction line, which is exactly what we've got there, okay? And again, the default behavior in matplotlib plot is it's going to join them, okay? So if I didn't put this argument marker there, it would just draw a straight line, okay? But to kind of show that it's actually dots that are connected, it's the X values and they're connected here. This is what we have, okay? You can also get, you can figure your residuals by doing the difference between Y and the predictions. Those are your residuals. You want to say, what's the mean of the residuals? We get 0 as we would expect. Histogram of the residuals, it should look normal, and it kind of does, okay? And it does, I should say, right? Plotted the residuals for diagnostics and things like that. Okay, so here's just a very quick example. There is a data set, the Boston housing data set. This, it's an old data set, and there's different variables and stuff. It is stored in Scikit-Learn in a format called a bunch, okay? And a bunch is basically a dictionary, okay? Except the dictionary, it's kind of like a named list, all right? So a bunch looks a lot like a dictionary. So it's got keys and it's got values, except the values are not limited to just being single numeric values. The values for data could be a matrix. The value for target is an array. Feature names is another array. Description is a bunch of text and stuff like that. Okay, so the Boston.data.shape, Boston.data itself is a NumPy array, 506 rows, 13 columns. The target is a NumPy array, one-dimensional array, 506 rows, no columns, okay? You can ask for the feature names, okay? And here's the description, okay? And this data set came from, is it the 70s or something, okay? And so they include, it's a little bit of a problematic data set, but so they include different, what they've done is, I guess they looked at different neighborhoods around Boston, and they measured different, different aspects about the neighborhood. Things like the, how many rooms per dwelling in that neighborhood, distances from the employment centers. So there's like different, there's like down, you know, the financial district and the industrial district, and, you know, what are the distances there? What's the tax rate, and different things. You know, some of these demographic stuff, you know, is a little bit troubling here. Okay. And so anyway, you might say, well, let's try to predict the stuff here, okay? So this is just a NumPy array. Okay, so anyway, what we're gonna do is I'm going to convert the data frame, or the NumPy array, into a data frame, okay? And this is the first 5 rows of the data frame. The names of the features are stored in this vector here in boston.featureNames. And so I'm going to just change the names of the columns to be the feature names, okay? So, so I'm basically just reassigning the columns to be kind of the feature names, right? And so now we get this data frame with columns that are appropriately labeled, okay? And here are the target values, and I'm going to basically add that here. Boston.price. Boston price is going to be the target value, so we add that. And so now here is our data frame. Okay. And we're going to just do Scikit-Learn to say, let's fit a linear regression model here. And we're going to say fit the x values are going to be everything from x to LSTAT, whatever that is, crime to LSTAT. Right. So this is pretty much what we had here. Okay. And then the then what we want is we want the target to be the target value, which is going to be the price. Okay, Boston.target will be that column. So we're going to fit x to the target, and we get that. You can ask for the coefficients, and it actually produces them, but again, that's not the point here. Okay, we can ask what were the predicted values here, and we can show the relationship between what we predicted and what the actual value is. And we get a fairly decent correlation here. We have, there is kind of this strange cap here in that the actual values for some of these things, the price is kind of capped, I think artificially, at 50 for whatever reason. And so, so you kind of get this thing going on there, okay? So when you look at the residuals, you also get kind of the effects of that cap and things like that. What's the overall score? The overall correlation, the R-squared value is 0.74 and things like that. And so, you know, you can do stuff like this. So anyway, that is just the very, very, very basics of using like doing linear regression with Scikit-Learn. So that's kind of your first thing here. And you know, if you're interested in doing this, right? If you're like, oh, let's so you can start by kind of looking through any of these things, right? You say like, oh, I want to do support vector machines for classification. That sounds kind of neat. And you look at this stuff, and you can always search the internet for more examples. The important thing, one important thing, is that Scikit-Learn always expects your X matrix to be numeric, right? And so if you have categorical predictors, you have to figure out a way to turn your categorical predictors into numeric values X. And this is a tricky thing, okay? Because what you can do is like you can turn everything into 0, 1 and 1 dummy vectors and dummy columns, 1 if it's a certain category, 0 if it's not, and things of that nature. But that may or may not be the best approach. So Scikit-Learn, a lot of these machine learning tools are always expecting the input values to be numeric, and it's a tough problem to think about, but that's kind of the state that we're in here. All right, we'll wrap it up here for today, and we'll see you guys next week. Have a good weekend, and we'll see you then. Oh, the quiz. I have not made a quiz yet. Ah. All right, we'll just we'll skip the quiz for today. We'll say no quiz. But thank you guys for tuning in, and yeah, have a good weekend. So we'll stop there.